For the inequality where the absolute value of x plus 8 is less than 11, we first subtract 8 from both sides to isolate the absolute value of x, resulting in it being less than 3. Think about what values of x have an absolute value less than 3, meaning their distance from 0 is less than 3. This forms a compound inequality where x is between -3 and 3. As a little trick to remember this, less than sounds like sand. Imagine x being sandwiched between 3 and its opposite. This can also be written using an AND statement, where x is greater than -3 and x is less than 3. To graph this, we put open circles at -3 and 3 and shade the region in between. For the inequality where the absolute value of x minus 5 is less than or equal to 2, the absolute value expression is already isolated. Remember, less than sounds like sand. So we use the sandwich method to write a compound inequality, placing the expression x minus 5 between 2 and its opposite. This shows us where x minus 5 results in an absolute value less than or equal to 2. To isolate x, we perform the inverse operation by adding 5 to all three parts of the inequality, leaving x between 3 and 7. This can be rewritten using an AND statement. X is greater than or equal to 3, and x is less than or equal to 7. To graph the solutions, we put filled-in circles at 3 and 7 since they are part of the solutions, and shade the region in between. For the inequality where 2 times the absolute value of x minus 16 is greater than -10, we first isolate the absolute value expression by adding 16 to both sides, resulting in 2 times the absolute value of x being greater than 6. Next, we divide both sides by 2 to fully isolate the absolute value of x, giving us the absolute value of x is greater than 3. Think about what values of x have an absolute value greater than 3, meaning their distance from 0 is more than 3. This means that x can be less than -3, as it needs to move farther away from 0, or x can be greater than 3. We can visualize this on a graph by placing an open circle at -3, shading the region to the left, and placing another open circle at 3 and shading the region to the right of 3, indicating that the values move farther away from 0. A little trick to remember this is that greater sounds like or, so this gives us an or statement. For the inequality where the absolute value of x minus 7 plus 6 is greater than or equal to 11, we first isolate the absolute value expression by subtracting 6 from both sides. This gives us the absolute value of x minus 7 is greater than or equal to 5. Next, we consider what values of x satisfy this condition. For the absolute value to be greater than 5, we can think of two scenarios. X minus 7 can be less than or equal to -5, moving farther away from 0 to the left, or x minus 7 can be greater than or equal to 5, moving farther away to the right. We then solve for x by adding 7 to both sides, resulting in x is less than or equal to 2, or x is greater than or equal to 12. To illustrate this on a graph, we put filled-in circles at 2 and 12, and shade the regions to the left of 2 and to the right of 12. This shows all the possible values of x that satisfy the original inequality. Sometimes there are special cases. For the inequality where the absolute value of x minus 6 plus 8 is greater than 5, we first subtract 8 from both sides of the equation, resulting in the absolute value of x minus 6 is greater than -3. Now, since absolute values are always non-negative as they represent distances, the inequality is always true for any real number x. Therefore, all real numbers are solutions. How about the inequality where the absolute value of x plus 11 minus 6 is less than or equal to -7? We start by adding 6 to both sides to isolate the absolute value expression, resulting in the absolute value of the quantity x plus 11 is less than or equal to -1. Now, the absolute values cannot be negative, so nothing can satisfy this inequality. Therefore, this inequality has no solutions.